Many of the inanimate objects around you probably seem perfectly still. But look deep into the atomic structure of any of them, and you'll see a world in constant flux, stretching, contracting, springing, jittering, drifting atoms everywhere. And though that movement may seem chaotic, it's not random. Atoms that are bonded together, and that describes almost all substances, move according to a set of principles. For example, take molecules, atoms held together by covalent bonds. There are three basic ways molecules can move: rotation, translation, and vibration. Rotation and translation move a molecule in space, while its atoms stay the same distance apart. Vibration, on the other hand, changes those distances, actually altering the molecule's shape. For any molecule, you can count up the number of different ways it can move. That corresponds to its degrees of freedom, which in the context of mechanics basically means the number of variables we need to take into account to understand the full system. Three-dimensional space is defined by x, y, and z axes. Translation allows the molecule to move in the direction of any of them. That's 3 degrees of freedom. It can also rotate around any of these 3 axes. That's 3 more, unless it's a linear molecule, like carbon dioxide. There, one of the rotations just spins the molecule around its own axis, which doesn't count because it doesn't change the position of the atoms. Vibration is where it gets a bit tricky. Let's take a simple molecule, like hydrogen. The length of the bond that holds the 2 atoms together is constantly changing, as if the atoms were connected by a spring. That change in distance is tiny, less than a billionth of a meter. The more atoms and bonds a molecule has, the more vibrational modes. For example, a water molecule has 3 atoms, 1 oxygen and 2 hydrogens, and 2 bonds. That gives it 3 modes of vibration: symmetric stretching, asymmetric stretching, and bending. More complicated molecules have even fancier vibrational modes, like rocking, wagging, and twisting. If you know how many atoms a molecule has, you can count its vibrational modes. Start with the total degrees of freedom, which is 3 times the number of atoms in the molecule. That's because each atom can move in 3 different directions. 3 of the total correspond to translation, when all the atoms are going in the same direction. And 3, or 2 for linear molecules, correspond to rotations. All the rest, 3n6 or 3n5 for linear molecules, are vibrations. So what's causing all this motion? Molecules move because they absorb energy from their surroundings, mainly in the form of heat or electromagnetic radiation. When this energy gets transferred to the molecules, they vibrate, rotate, or translate faster. Faster motion increases the kinetic energy of the molecules and atoms. We define this as an increase in temperature and thermal energy. This is the phenomenon your microwave oven uses to heat your food. The oven emits microwave radiation, which is absorbed by the molecules, especially those of water. They move around faster and faster, bumping into each other and increasing the food's temperature and thermal energy. The greenhouse effect is another example. Some of the solar radiation that hits the Earth's surface is reflected back to the atmosphere. Greenhouse gases, like water vapor and carbon dioxide, absorb this radiation and speed up. These hotter, faster-moving molecules emit infrared radiation in all directions, including back to Earth, warming it. Does all this molecular motion ever stop? You might think that would happen at absolute zero, the coldest possible temperature. No one's ever managed to cool anything down that much, but even if we could, molecules would still move due to a quantum mechanical principle called zero-point energy. In other words, everything has been moving since the universe's very first moments, and will keep going long, long after we're gone.